that didn't help. I am trying to, oh, there it is. Trying to fix the way that I'm live streaming. I had an issue yesterday where I accidentally recorded over my own YouTube video. I didn't even know I could do that, but I did it, so that was fun. This is a learning process, I suppose, and I am not perfect at live streaming. I suppose that's why I don't have 1,000,000+ hits on all of my videos yet. Of course, I also don't have a fun catchphrase like, "Allow us to commence." Allow us to commence, my friends. We are about to have some fun. Okay, whatever. I'm gonna start teaching. Alright, so this is EGR 325. I screwed up yesterday and overwrote this lecture, so I'm re-recording it. So if you did watch the lecture already, you've already seen this. If you did not watch the lecture already, you lucky ducks, I am recording this again for you, just because we're best friends. We'll go with that. By the way, my birthday's next month. Buy me cake. I'm kidding. I don't like cake. Okay. No, I'm kidding again. I actually do like cake. But I like ice cream cake more. Yeah, I swear I had something for class today. Anyways, let's talk about some equations. So, just to refresh your mind, what I'm going to do is I'm going to go ahead and pull up my good friend Microsoft Paint, because who doesn't want to watch a lecture in Microsoft Paint, am I right? We're talking about the ultimate of quality here. Like, I spare no expense to make this the single greatest lecture of your life. I'm not sure if I'm sick with tonsillitis at this point or delirium. Believe it or not, this is actually me normal. That's terrible. I should drink more cough syrup or something. Okay, so let's talk power and energy equations. So, I did give these to you yesterday. I'm just going to give them to you again because why not? It's just so much more fun in an environment where it's terrible. It's a horrible rendition. P is equal to the time derivative of energy. And this is true for every system. It's true for all kinds of energy. It's true for all kinds of power. You talk about electrical power, it's the time derivative of electrical energy. You're going to talk about gravitational power, it's the time derivative of gravitational energy. You know, there's so many things this equation relates to. For the purposes of this class, we are only going to be dealing with electrical power, and if I use the term P, it refers to electrical power. If we do have mechanical power, such as using it with a motor, which I don't believe we're going to be using any motors this semester, but if we did, I would refer to it as something other than just P. I would like P mechanical or PM or PHP or something, you know, just something to designate that it's not electrical power. For the purposes of this class, anytime you have the word P, first of all, it is a time derivative of energy, but second of all, the second equation that goes along with that is that power is equal to voltage times the current. Okay. So let's pop up our good faithful friend here, Microsoft Office Excel, because what better pairing for a lecture is some Microsoft Paint with some Microsoft Excel. Boy, you are living the high life here, my friends. I just you're welcome. It warms my heart to teach you in such freely cheap ways. I just wish I could do this in person. I wouldn't be using Excel. We'll go that far. But there are some things that we can talk about here in Excel, and there is an actual benefit here to using Excel because I do enjoy graphs, and graphs are very helpful. So let's say we have an energy versus time curve. So this is time in seconds, and this is energy in joules. Those are the units for both of them. We're going to go ahead and start at 0. I'm going to have it piece up by 0.1 seconds. We'll have it go to 2. Okay, and then for energy, we'll start at 0, 0, 0.25, 0.4, 1.2, 2.0, 2.1, 2.15, 2.17, 2.18, 8, 6, 2.12, 2.04, 2.84, 2.64, and then we'll finish off with I don't know, 2.54, something like that. Okay, so basically what this represents is, let's say I took some measurement instrument. This would probably be a multimeter or something with the ability to do the measurement. Energy is kind of a derived calculation. It's impossible to measure energy directly. You have to derive it from a measurement. So it's a calculated value. But we calculated this number of joules of energy at X time for some item. Okay, this could be a measurement of the amount of heat energy that's stored in an item, where we set it relative to 0, which is the initial heat state. This could be the amount of light that's contained in a room. This could be the amount of I don't know, sound levels that are being added to a room. It could be something. Okay, it's just some energy value. And what I'm going to do here is I'm going to go ahead and insert scatter plot, which already figures out what I want to do with it. Oh, gross. Why do you suck? Oh. Yeah, oops, my bad. All of these were supposed to be ones. Such a beautiful line that I drew in my mind too. Oh well. But you'll notice this is the energy versus time curve. Okay. Now what I'm going to do quick is I'm going to change chart type, set it to lines, and look, there we have a graph. Now this is what's referred to as a discrete system. You'll notice this isn't a function. This is actual physical measurements. These are all data points that I would have collected. Now the difficulty here is, go back and look at our equations here, I have to be able to take the derivative of that. Well, there's no derivative. This isn't a function. What's the derivative of 1.8? Well, this is where you kind of have to use your discrete calculation methods. Discrete calculation methods are fun. Basically, it was introduced in calculus as a way of handling derivatives when you do not have an exact system. And basically the formula for it is you have delta energy divided by delta time. Okay. Now this is a big shift from dE dt. It's a delta and a delta. A delta represents a finite quantity, whereas a d represents an infinitesimally small quantity. What does that mean, Kale? Well, it just means that when we go to do a derivative here, what we're doing is we're taking this change between these two numbers and dividing it, between these two numbers, and we're dividing by the change between these two numbers. Okay, so I'm going to go ahead and calculate the derivative this way. Actually, I'm going to do it one up. Is equal to, parentheses, this minus this divided by toot toot. Oh, gotta remember that parentheses. This divided by that. Ta-da! Oh, look, it's a 0. Delicious. Oh, that's not on. Divided by, it's supposed to be a minus. There we go. Now we'll just go ahead and drag this down. Okay? Now what does this represent? This is the derivative. And why did I take the derivative of energy with respect to time? Well, if I go back here, the derivative of energy with respect to time is power. So if this is some energy value, electrical energy or thermal energy or something, by me taking the derivative, what I've done is I have calculated the amount of power that is related to this energy system. So I'm going to go ahead and just relay this back into the correct units, which is power and watts. Okay, so what we'll have here is, you'll see that here energy is increasing. When energy increases, we go whoop. We can see here that the derivative is pretty constantly up. This upward derivative is, it's a sign that there's an increase in the amount of energy. The increase in the energy it causes a positive slope in that line. Because there's a positive slope, the derivative is positive. Because the derivative is positive, we have positive power. And the higher that slope is, which right here that's what, 4, the higher that slope is, the larger the amount of power. So what we have here is that the energy is changing, and as the energy changes, we can detect power. If the energy is constant, like it is between here, well, power is supposed to stay constant, but here power is being put into the system because the energy changes in the next step. That's just a discrete way. Really what happens is that each one of these points, that's not a real point. Each one of these points is inserted between each of these. That's just a way that doing a discrete derivative reduces the number of data points that you have by 1. That's just the way it happens. But in integrals, you can get away with not doing that, but it's still kind of gross. You still actually can lose one in an integral too, but discrete methods are just, they're harder, but at the same time, we didn't have a choice because I didn't have a function here. But we did calculate what the derivative of power, what the derivative of energy was when we calculated power. Now I can take this, I'm going to go ahead and copy it, paste, and then I'm going to go in here and change the data. Let's see, I'm going to change the name up here to this one, I'm going to keep the x values the same, and then I'm just going to plot power. Okay. Now you'll notice that the power graph is a little grosser. It's not as pretty as this one, because the power is not. It's a derivative, and this is it being a discrete function. Power is just not going to be nice, especially since we have a resolution of what, the 100th. I mean, 3 decimal places at most. So we're not going to get a pretty power curve with that level of resolution. But this shows what is the derivative here. You'll notice that it's positive. It's at a very large positive value about right here. If we line that up, that's here where the slope is the most positive. Up here it goes down to 0. You'll notice here it goes down to 0. And then it dips down into the negatives. And the dip down into the negative corresponds to the fact that the slope becomes negative. So what does that mean? Well, it means we still have positive energy in the system the whole time, but because of the way that power works, because it's a derivative relationship, we have negative power at the end of the system because power is actually leaving whatever this component is. So for the very beginning, the energy in the component is changing, it's becoming more positive. If this is a resistor, it means that the heat generated by the resistor is increasing. If this is also a resistor, it means that there is a back surge where the resistor is actually being negatively powered at the very end. That's what this means. In here, means that the energy in the resistor is increasing and suddenly decreases. So that's kind of impossible for a resistor. It would be possible for a capacitor, for an inductor, but that's what this effectively means. So that's how you can calculate. It's one way of calculating power. You just take the derivative of energy. You can do the flip side too, where you do a discrete integral of power. Similarly, if we had an equation for this, like let's say this was I don't know, 2.5 times, oops, I gotta put an equal sign, equals 2.5 times sine of, I don't know, this times 90. Okay. It automatically calculates this in degrees. So if I were to change these values, ooh, nice. That's kind of gross. Let's change this away from 90. I don't really want to have to deal with 90. We'll just try it as times 1. There we go. There's a nice little curve. Then what I can do is, instead of calculating a discrete, I can just mathematically derive what the equation is for the derivative of energy. And if I do that, then this is what? 2.5 times cosine. And then I can copy this down. Excuse me. And you'll notice that, once again, starts off positive. Here it starts off at a maximum positive, then goes negative because the energy does decrease at the end here. So keep that in mind. It's two different methods of calculating this. Both of them it's the same exact method. It's the same exact formula here. Power is equal to the derivative of energy. So if you have energy, you can derive it to get power. Similarly, if you have power, you can take the integral and get energy. If we did take the integral here, integral, this would be positive because there's much more area up here than there is down here. And if we know the starting condition is at 0, 0, then we can add this starting at 0, 0. But that's what's needed to do the integral there. So this is just a little bit of a review on integrals and derivatives, which I'm sure everybody wanted to do. But now we can play around with another piece here, and that is, what if we're given, as a function of time in seconds, what if instead we're given voltage in volts and current in amps? So here, once again, we're going to put 1. Just going to go ahead and add it by 1. We'll go to 3 this time. Voltage, we'll say this time voltage stays constant at 5 volts. Okay, and here we'll say current. We'll say current is a function, but we'll say it's an exponentially decreasing function that maybe starts at 25 milliamps and exponentially decreases down to 0. Like that. There's a function. So what I'm going to do first is I'm just going to plot all of these, because why not? Notice that this starts at 0.025 and decreases down to 0.045. So it is decreasing. Means if we were to draw a chart, we can kind of guess what the chart's going to look like already. Here it's already given us our two data sets. So if I go back and select data, it's got the current, the voltage. It already knows what each one of them wants. If I go ahead and shut off voltage, that is not what the current does. That's actually backwards. Nice. Starts at 0.025. Oh, it increased. Oh, dang it, Kale. Gotta put a negative sign in here. It does increase, though. There we go. So now it decreases. I can change this chart type again, just because I like lines better. This is what the current looks like. If we go back and look at just the voltage, which I can do by switching the data type here, you'll notice that the voltage is constant. And it does stay at 5 volts the whole time. So how do we calculate the power at time equals 1 second? How much power is being consumed at 1 second? Well, to do that, what we have to do is we just simply take the equation that we have, which is, whoop, that's Streamlabs. We take this equation right here. Power is equal to voltage times current. So I go in here and I've got voltage and I've got current, and I can say, okay, well, it's equal to this times this. Nice. So there are 0.1023 watts of power being generated at 1 second. Even though the voltage is constant, the reason why it's not a normal number is because we do have that current that is decreasing. So keep that in mind. Now, how would we get the plot of the shape of the power function? Well, we would have to calculate power at every single one of these points. I'm just going to have Excel do that for me because, you know, what am I, a plebeian? And then I'm going to go ahead and I'm going to add this plot to the graph. Just for sake of completeness, X values. I have my Y values. For some reason I didn't grab the bottom one. I don't know why. I will grab that one. And there we go. Now we have two graphs. And this one, no values. I'll just fill it in. Now, where's my second graph? Dang it. I should be seeing it. It's not there. Oh, it's because once again, I struggle with simple things like, you know, hitting the enter button. So there we go. This is our power curve and this is our current curve. You'll notice they have a very similar shape. It's because, quite frankly, it's you multiply this by a constant and you get this. It's going to have the same shape. Alright? That's what happens when you multiply by a constant. But that's our power curve right there. And so at any point, if we want to know what the power is at 0.5, we can just go to 0.5, look at the value for that curve and say, okay, well, there's 0.1131 watts of power being consumed at 0.5 seconds. There's 0.1 watts being consumed at 1 second. There's 0.0686 watts being consumed at 3 seconds. And that's what we can do to calculate power. So it's pretty straightforward there. All we need to know to calculate power is if we have the voltage and if we have the current, we just multiply those two values at that time together, and we have our power. And that's all it takes to calculate the power. Now, there are a couple of other things that we can do. Let's say we know. Now I'm gonna get all funky here for a second. Let's say bop, shoo bop, and shoo bop. Let's say we know that the voltage, let's say it fluctuates. It starts at 5, but it's also 5.1, but it's also 5.2, but it's also 5. It's also 5.1, but it's also 4.9. It's also 5. You know, and what if we just take this pattern here and we continue to repeat it? This actually just steadily decreases for some reason. Whatever. 4.9, 5, 4.8, 4.9, and let's say this is our measurements here. 5, 5, 5, 5.1, 5, 5.2, 5, 4.8, 5.2, 5, 5, 5, 5, 5, 5.1, 5, 5, 5.1. There we go. Okay, so that's what we measured for our voltage. The thing is, we need an exact amount of power. We need 12.5 watts. Okay? And we do have a varying voltage here. What this means is if we're going to get an exact amount of power out of this, and we do have a slightly varying voltage, what does it mean for our current? Well, our current's going to have to change in order to make sure that we get the right amount of power. Remember, we only have three variables here. If we say we need 12.5 watts of power, and we have 5 or 5.1 or 4.8 volts, then what does it mean for our current? What does our current look like? Well, it should be mostly constant, right? Because this is a mostly constant number multiplied by another number is equal to a constant number. This should be at least mostly constant. At least that's what our expectation is. Here, because we already know power and because we already know voltage, well, if we can just modify this equation, solve for I is equal to P divided by V. So we just plug that in here. So this is equal to that divided by this. It's 2.5 amps of power is what's needed. Now this is a power calculation for a Raspberry Pi. You'll notice that at some points the current dips down and at some points the current actually increases to 2.6. You'll notice that there's a little bit of wave here, but it tries to be mostly constant. But we can use this formula really anywhere. In a discrete system, in a formulaic system, this is how we calculate power, and we can calculate voltage or current if we know the power. But really power is kind of the guiding principle here, where we have to know power one way or another, and to know power you got to know voltage and current. Power is such a critical concept in all of physics and in all of engineering. Understanding power, understanding energy, that really we are going to focus a lot on power in this class. So hopefully you've had a little bit of a refresher. Hopefully you feel a little bit more comfortable with doing power calculations now. You are going to have some power calculations on your quiz that is due next week. But aside from that, that's all I have for today. I will see you tomorrow. I'll let you know on Canvas whether or not we're doing it virtually or in person. I'm really hoping to do it in person, but that does require me to feel good. And as of yet, I'm still coughing and I'm still really struggling to sleep. Well, I just want to take a nap constantly, but